And to get us started, I couldn't think of anyone better. Abhinav Jangda is going to tell us about fast matrix multiplication. Abhinav is my colleague at Microsoft. I get to learn from him every day, and now you have the awesome opportunity to learn from him now. So take it away, Abhinav.
Thank you, Tyler. Thank you everyone for coming. So today I'm going to talk about subcubic matrix multiplication on GPUs. Just to start, so we know matrix multiplication is very common, and to set the notation which we'll be using in this talk, a matmul takes two matrices A and B, and A is of size m cross k, B is of size k cross n, and the output C is of size m cross n. So we are going to represent this matmul with m and k, these three sizes. And it's a very common operation. We see it is being used in scientific computing, where we have large float bitwidths, and also in machine learning, where we care about smaller, low precision types. And so how do we compute this matmul? Well, it's usually done using this three-loop cubic algorithm that we are all familiar with, m and k. And over the last several decades, highly efficient parallel implementations of this cubic algorithm have been developed for CPUs, for GPUs, and these are very efficient that they obtain close to peak flops. So the question becomes, if they are very efficient, can we even make matmul even faster than that? And that is what I'm going to talk about, that our system SubCuber, it can make matmul faster up to 23% than NVIDIA libraries. And as you can guess, it uses subcubic algorithms. So a very common example of subcubic algorithm is the Strassen algorithm, which we have always, I'm so sure everyone has learned about that. And it runs in n to the power log 7 base 2, which is n to the power 2.8 complexity. So how it works is it's a recursive algorithm. So at every recursion step, it's going to divide these matrices C, A, and B into 4 parts: C0 to C3, A0 to A3, and B0 to B3. So if we apply this recursion step once, we are going to get, instead of 8, we are going to do 7 smaller multiplications. And theoretically, since we are doing 7, not 8, so we can get 12.5% speed up over the cubic algorithm. Let's do it again. So in that case, we'll have 49 of these smaller matrix multiplications. That would mean 23.5% speed up. Now the question is, how do we actually execute this on a GPU? Now there are several Strassen algorithms, and one of those algorithms is a Strassen-like algorithm. Which has some input summations that you see on the left hand side, and then it does 7 smaller matrix multiplications, and then it does some output summations. So let's look into this particular M4 that takes this I1 and I5 as input. So I1 is A2 minus A3, I5 is B1 minus B0, and the output of M4 is used to update C3 and O3. And there are several Strassen family of algorithms. The original Strassen algorithm, which was probably the first subcubic algorithm, had these 22 input and output sums. Then the Strassen-like has 15. Alternative basis Strassen, which is the latest one, has 12. And as you can see, since with the decrease in input and output sums, the maximum absolute error as compared to the cubic algorithm also increases. So which Strassen algorithm is best? It depends on your application. If you want, you can trade runtime and numerical stability based on the application. So how do we execute these Strassen algorithms? Well, a very common baseline, a very old baseline, was to execute 9 different kernels. So the first kernel, CUDA kernel, is going to compute those input sums. The next 7, it's going to compute the 7 matrix multiplication, and the last kernel is going to compute some output sums. But this approach is always slower than NVIDIA's libraries for float 16 and very large sizes, up to 16,000. And the reason is simple, that the first and the second kernel, the last kernel, they can take up to 50% of the total time, because what they are just doing is reading a memory, computing something, and writing it back. So the problem is not actually the summations here. The problem is the memory excesses, and how can we avoid that? And the situation becomes even difficult at L is equal to 2, because then they are going to have 51 of those smaller kernels. So how can we optimize those manually? And that is why I think a compiler approach was the right call here. So SubCuber is a compiler that takes a Strassen-like algorithm written in PyTorch API. It will extract that graph of the PyTorch. It takes data type, the metamal sizes, and the GPU spec, and outputs a efficient CUDA code. And it has several passes, like it generates an IR, it generates a kernel schedule, does a lot of fusion to generate that code. And that is why it performs significantly faster as compared to NVIDIA supplied Cutlass and cuBLAS libraries. For example, float 32 is up to 23% faster, float 16 is up to 16% faster, and the sizes in this LLM that we see, like Llama, Phi, and Qwen, those are also up to 16% faster. So let's look into detail how SubCuber works. And the first pass of the SubCuber is to create that IR. So it will go through the Strassen algorithm and create 4 AST nodes. So the first is, well, input sum. We are going to compute an input sum node. The other is a matamal node that represent each submatamal. The next is a combined input sum and matamal node. And the last is a Strassen node. So that represents all of this Strassen algorithm. Now each of these nodes map to a different SubCuber kernels. One is, which can compute an input sum, which is K1 kernel. The other is we can compute a submatamal through the K2 kernel. And the last is a K3 kernel that computes both input sum and the submatamal. And then there is a K4 kernel that computes the Strassen on each algorithm on each tile. So I'm going to talk about K3 and K4 because they are the most interesting. And all of these kernels follow the same tiling methodology that we all know of. We divide that output C into different tiles of the same size on 2D blocks. And to compute a tile, we only need to load that portion of A row and that portion of B column, nothing else. So each tile can be executed independently of the others. But the point here is each tile is also computed serially. So there is a long loop of K inner dimension that has to be done. And that is how the K3 kernel actually works. So the K3 kernel, it is not only going to compute a submatamal, but it is also going to compute input sum for all other submatamals so that the other submatamals don't have to do anything. And if you look in the Strassen-Vinograt algorithm, we see this particular M0. M0 is just A0 multiplied by B0. It doesn't require any input sum. So on the figure that you see in the down, so M0 is being computed with A0 and B0, and each iteration of the K loop, it's going to the kernel is going to load some part, a tile of B0 to B3, a tile of A0 to A3, and then also going to write a tile of I1 input sums. So by interleaving these memory accesses with the computation, we can actually overlap these memory accesses for input sum with the computation, and that reduces the input sum time by 2 to 5 times over the separate sum kernel, and achieves almost the same you would expect the memory bandwidth of the GPU. The next kernel is the K4 kernel, and it works on each tile. So let's zoom into one tile, and it divides this tile into 4 parts. It divides the A into 4 parts, divides the B vector into 4 parts, and then run a Strassen algorithm on each to compute that tile. Now, all of these I1 to I8, they have to be stored into the cache, so because they are being used through M0 to M6. But it also only loads A and B from the cache. So there is no more memory accesses here. We just don't have any other memory accesses. So if we look on these 2 kernels, we can think of these as kernel schedules. So for level is equal to 1 for the first recursion level, we have 2 schedules. One is, we do the K3 kernel, which is compute both input sum and submatamal, and the others are K2 kernel. And the good part about this schedule is it can give good performance on large matamal sizes. But because these are 7 smaller kernels, it is bad for small sizes, because on small sizes we want single kernel, and that is where the K4 schedule works fine, where is a single kernel. It gives good performance for small matamal sizes, but it's bad for large matamal sizes as it has high cache usage. now we can think of these schedules as actually transformations. And if we recursively apply these transformations, we can get higher level schedules. So as an example, consider L is equal to, consider that we want to get schedule for 2 levels. We want to apply Strassen algorithm twice. So first we apply the transformation 1, which is we convert a matmul node into 6 smaller matmul nodes. Then we can convert these 6 smaller matmul nodes into some other transformation. So let's say M1 to M3 are being done by this transformation that uses Strassen MM node, while all others can be done with this other transformation, which we have already seen. So since there are just 2 transformations and there are 6 cases, with each level the schedules are just exponential. For L is equal to 1, we have 2 schedules. L is equal to 2, we have 64. L is equal to 3, we have so many. I didn't even calculate that. So SubCuber has this greedy algorithm which we can look into the paper and with a cost function, and that is how it finds the best performing schedule. Now these kernels are basically based on NVIDIA Cutlass, which is a library by NVIDIA that has a highly efficient cubic implementation. And these kernels right now supports Ampere and Hopper architecture. So they have CUDA cores, tensor cores, different floating point types, different ways to transfer from global to shared memory, etc. Now let's look at some evaluation. And here I'm just going to talk about H200 results. There is also results for A100. Those are in the paper. And the baseline here is definitely NVIDIA Cutlass, which we want to beat. And the other is this previous work of fused InSum that fuses input sum loads in each submatmul. And that is always faster than the separate sum kernels. So I'm not going to present results for that. And there are more baseline paper like cuBLAS and cuBLAS LT. So first, let's look at some square matrices for floating point 32. And on the right hand side, the graph has the x-axis. So the x-axis is the size of the matrix, and the y-axis is the performance improvement over Cutlass. And the orange lines are the one that represent SubCuber for first level and the second level, and the fused InSum are the blue lines for first and the second level. And as you can see, that the SubCuber reaches theoretical speedup of 23% at size 3584 and more for 2 level, and also the similarly 11%, 12% for first level. While the blue lines, which are for fused InSum, they never reaches the theoretical speedup. So they are only 16% for the second level, for example. More interestingly, the SubCuber is faster for 512 and higher size, which is 3 times lower than what it was for fused InSum. So ideally, we want to push this graph as to the left as much possible, so that it is faster for as small size as possible. So right now, it's possible to do with 512. And we also have this float 16 results that uses tensor cores. The problem with tensor cores is the tensor cores are 16 times faster as compared to the CUDA cores. So the memory to compute ratio changes drastically. And that is why the size where SubCuber is faster is 4096. And although for first level it reaches around 11% or 12%, but for the second level it is only 16% faster. So there is still a gap to do. Then we also picked some matmul sizes from different LLMs and tried SubCuber on those matmul sizes. So we have Llama 3, 5, 4, and QN3, and these represents these 3 LLMs represents different small LLM, medium LLM, and a very large LLM. So I'm going to just show this improvements for Llama, and we can refer 5, 4, and QN3 in the paper. And so Llama has 2 matrix multiplication, MM1 and MM2. And on the graph on the right, the bigger graph on the right shows the speed up over Cutlass for batch size 1 to 32. And as you can see, the MM1 reaches 16% for the biggest batch size that Llama 3 can support. And that is because MM1 is very, very big and we can apply 2 levels, while MM2 reaches 12%. And this leads to a faster end-to-end inference of 4 to 8%. Now, It's not just, so I only presented for Strassen-Vinograd, but we also have similar performance for all other Strassen algorithms. While the existing works, they were only focusing on optimizing a particular algorithm, for example, Strassen-Vinograd or the Strassen algorithm, and they were designed when the tensor cores were not even present. While the SubCuber supports all of these and provides very good performance. So in summary, I think it's possible to have subcubic matmul on GPUs, and I'm happy to take any questions. Thank you.
All right, let's see, Ganesh has a question.
Yeah, very nice talk, Abhinav. Yeah. So long ago when I heard Strassen, I asked my numerical friends why is it not being used, and they said it's the error.
Yeah.
So I looked at your paper and you have L2 norm error,
Yeah.
but there's also a problem of backward instability. So in your experience, is this mainly meant for machine learning or for HPC? Because the acceptance of these algorithms will depend on what they're looking for in terms of error.
Yeah.
I want to understand. I'm not an expert, but I want to see your opinion.
Yeah. So for first in machine learning, we have seen several works that actually have way higher error rate as compared to the Strassen algorithm. So it should work. But in my experience, if we just train with this algorithm, with this implementation, and do inference, it should be fine. But the problem is, training with one algorithm and then doing inference on the other algorithm. For respect to the scientific computing, I'm not so sure about that. I'm not much aware of it. But the recent papers show that for float 16, for float 64, the error rate is anywhere between 10 to the power minus 9 to 10 to the power minus 7. So I don't know, it might be okay, yeah. Yeah.
Great talk. Did you compare this algorithm with stream K or split K kind of matrix multiplication?
So those NVIDIA Cutlass results are the best that they could possibly do. Yep.
And another question I have is the end-to-end inference. So the performance is not as compared to the GEM performance. So is it because of the launch latency, because you're launching these tiny kernels, and that takes basically start dominating when you have these small gems?
I didn't understand the question, actually.
That's okay. We'll take it off.
Okay, that's fine, yeah.
Ahmed, do you want to start setting up real quick while we take the last question?
Yeah, very cool talk. Thank you so much. I wanted to know, I like the results you had with FP16, and you pointed out that that requires a larger K before there's an advantage, because basically the base speed up is smaller. If we go even lower precision, right, FP8,